All right, so welcome. So hopefully the quiz went well. Finally, we're back to normal. No exams for a while. Now it's just steaming through calculus. So let me share my desktop and we'll go over the quiz. Okay, so here's the quiz. The first question was, let's suppose we have f of x equals 1 minus x, 1 minus 1 over x plus x times x cubed plus 5x plus the square root of x. Find f prime of x. Okay, the hard way of doing this, which I'm hoping none of you did, is multiply this messy thing out and then use the power rule and everything. What's the easier way of doing this particular derivative? So what's the way you should do this derivative?
Product rule.
Yeah, this is definitely the product rule. So what I'm going to do is I'm going to use the product rule. And I think the easiest thing to do, since we're on the computer, is I'm just going to put a prime there. I'm actually going to copy this. I'm going to go plus. I'm going to paste it because the product rule is the derivative of the first times the second plus the first times the derivative of the second. So what we have to do is we have to take the derivative of the first. Okay, first thing, I hope you all know, what's the derivative of 1?
0.
That's 0. That's just gone. All right, derivative of 1 over x. It's easier to write that as x to the negative 1. So what's the derivative of negative x to the negative 1? And use the power rule.
1 over x2?
Yeah, 1 over x squared, or even easier, x to the negative 2. Easier to type. And then the derivative of x. That's easy.
1.
1. Okay, so I just did the first part. We now have f prime, the first prime times the second. Now we're going to take the first times the derivative of the second. What's the derivative of x cubed?
3x squared.
3x squared. Derivative of 5x is?
5.
5. And then the derivative of the square root of x is x to the 1/2. So the 1/2 goes outside, and it's times x to the 1/2 minus 1, and the half minus 1 is negative 1/2. And that's it. There's really no work to show here.
Are you kidding?
And there's f prime. Question?
That's where all my time went, was working it out from that point.
When you were done.
Wait, Larry, I thought you were supposed to multiply it out. That's what I was taught. Like with the videos and stuff, you have to multiply. You have to like multiply it out.
Oh, definitely not.
That's it.
Oh, no. I mean, we got to do question 2. We're not done yet because we have a question. No, I've mentioned it many times. So I'm going to mention it probably many more times before it finally sinks in. Is that what must you always do in this class?
Calculus.
And what do you not have to do if you've done the calculus?
Algebra.
Uh-huh. So have I done the calculus?
Yes.
Good. That's good enough.
Okay.
Is that clear? Yeah, the last thing you would want to do is multiply this horrible thing out.
So for those of us that did multiply this horrible thing out, are you going to give us full credit?
It means you ran out of time. That's what the problem is. You get full credit if you actually got through the whole thing. You know, got through problem number 2. You got to get to number 2. Why do the simple questions confuse you? I'll tell you, that's one of the things about math. It's really easy to watch, and it's a lot harder to do. So you're watching it, and that's why it looks so easy. And no, I didn't do anything tricky, did I? I used the product rule, and you knew the product rule is going to happen in this quiz because that's what we talked about. And guess what? Let's look at question 2. And what rule do we think we're going to have to use for question 2?
Wait, really quickly, can you leave the negative numbers in the exponent?
Sure,
That's
because
okay.
changing it would be algebra, right?
That's true, yeah.
My rule is you have to do the calculus. Okay, what you can't do is just, look at this and say, well, I'm going to put a prime on the first one and I'm going to add the second one with a prime on the second one. Because then you haven't done the calculus, you actually have to do the prime. Does that make sense?
Yeah.
But once you have done the calculus, which is take the derivative, then you're done with the problem. Okay. Now the next one we'll get to a little bit more because of the question. So find the values of x where f of x equals 1 minus 2x over 1 plus 3x has a horizontal tangent line. So how do we decide where a function has a horizontal tangent line?
When it equals 0.
Not when the function equals 0, but when
The derivative equals 0.
the derivative equals 0. Good, good. Maybe you're right with when it equals 0, but the word it needed to be changed to, should be, defined well. Maybe you were thinking derivative. So it's not when the function equals 0, it's when the derivative equals 0. So guess what we have to do? Take a derivative, right? Okay, and I should let you know, pretty much for the rest of this entire class, if you haven't taken a derivative, you probably didn't do the problem right. Okay, that's all we're doing for the rest of this whole class, is we're taking derivatives, but there's a lot of stuff you don't know how to take derivatives of, because we certainly don't want to use a limit definition every time. We want to leave that, okay? But I'll use that to prove a few things, but you want to be able to take a derivative of anything. And right now, do we know how to take the derivative of anything without using a limit definition? Of anything that's differentiable? Okay, and the answer is no. Okay, you don't know, for example, what's the derivative of the tangent of x? I bet you have no idea. Okay, and the last thing you want to do is jump into the limit definition. It would be horrible. So we're going to spend a lot of time finding derivatives of things that we haven't done yet. But this one we've done. We need the quotient rule, because one thing you should expect it's a division. So you know that's coming. And hopefully you remember the poem. What's the first word in the poem?
Low.
Low. So I'm going to take 1 plus 3x. And just copy it. And paste it. There's my low. And then, what's the next piece of the poem?
D high.
high.
D high. So what's the derivative of 1 minus 2x?
-2.
-2. Okay. And then, what's the next word in the poem?
Minus.
Minus. And then?
High.
So that's the 1 minus 2x. And then what's the next word in the poem?
D low square.
Not d low squared. Simpler. Fewer words.
D low.
Just d low. So what is the derivative of 1 plus 3x?
3.
Okay, and then how does the poem end?
Square the bottom.
Square the bottom and away you go. So I need to square the bottom. Any questions about that? Am I done?
No.
No. So this is when you do have more work to do, not because I'm making you simplify. I don't care if you simplify or not. But what was the question? We want to find out when it has a horizontal tangent line. So what do I do with this derivative? How do you find whether you have where you have a horizontal tangent line again?
Set it as equal to 0.
Yeah, we set this derivative equal to 0. So let's do that. That was easy, right? Now we need to solve. So I'm just going to copy and paste. And adjust. Okay, if a fraction equals 0, what do you know?
The denominator goes away, cancels out.
Yeah, exactly. The denominator cancels out. So let's do the following. We can have the numerator equal 0. Any questions on that? Okay, so now I'm going to take that numerator and let's simplify. So to simplify, what I'm going to do is I'm going to look at the things that don't have x's and the things that do have x's. So on the first term, we're going to get a -2. On the second term, we're going to get a -3. So -2 minus -3 is, I say -2 plus -3 is -5. And now let's do the x terms. We're going to have a -6x, and then we're going to have a minus, that's a plus. Let's see if I got this right.
Yeah, I was wondering because the 6 x's cancel out, so you can't really factor if there's no x.
Exactly. So we'll get there. It's not factoring, we're just simplifying. So those cancel out. So what do we get? We get -5 equals 0. Is that clear? Any questions on that? So what is the solution to -5 equals 0?
There's none.
No solution. So what's the statement that we should write?
Does not exist.
Yeah, or there, it's not quite does not exist, because the question is, where is the horizontal tangent line? And there, what values of x? And there are no values of x with, where, I guess, the function has a horizontal tangent line. Any questions on that? Any questions? Okay. The reason why I gave you this one, I know it looks a little weird at the end, is that anything that has a nice horizontal tangent line that uses the quotient rule would have been too long for the quiz, and I tried to make the quiz not too long. Although, if you multiplied this sucker out on problem 1, the quiz is too long for you. Any questions at all on this? Okay, so now that we understand the quiz, let me go back to our agenda. And are there any questions about anything? Hopefully you're all getting good at the product rule and the quotient rule. And the power rule, of course. Any questions? Okay, if there's no questions, let's start talking about this next section. And the next section starts out with the tangent line approximation. So I have an example here. So if you have y equals -x² plus x plus 2, good old parabola, and we want to focus at x equals 1. So the first thing is, and I'm hoping you can all do this, what is the equation of the tangent line? I'm going to give you a minute or two. I want you to try this. because this is very important that you know how to do this, and then I'll do it too, but I want to give you a shot at giving it a shot. So sit down, pencil and paper is fine. This isn't a test or anything, but let's see if you can find the equation of the tangent line to y equals negative x squared plus x plus 2 at x equals 1. And it's not a trick question or anything. It's something you should all be able to do. So give it a shot. I'll be quiet for a minute. And when you have it, put your answer in the chat box. And we'll see if you're right. But hopefully y'all get it right. Getting a few different answers, so let's see if we'll end up with most people having the right answer. I think I've seen 5 different answers already. And there's only one answer, by the way, and I'll get there. Everyone's got something different. Okay, it sounds like I need to show you how to do this. Okay, so the first thing, if you want the equation of a line, what 2 things must we have to get the equation of a line? This is basic algebra, not calculus.
Slope and a point.
Yeah, slope and a point. Okay, now let's go to calculus. The slope of the tangent line, what's another word for that? Start with the D?
Derivative.
Yeah, most important word of the whole class, derivative. So let's find out what is y prime. And again, this is not a trick question. This is supposed to be an easy y prime. So y prime equals, we can just use the power rule. What's the derivative of negative x squared?
Negative 2x.
Negative 2x. What's the derivative of x?
Plus 1.
1.
Plus 1. And what's the derivative of the 2?
0.
0. So y prime equals negative 2x plus 1. And we need it at x equals 1. So y prime of 1, well, just plug in. And when you plug in 1, what do you get?
Negative 1.
Negative 1.
Negative 1.
So there's our slope. All right, now we need a point. Well, the x-coordinate is 1. That's given. How do we get the y-coordinate?
Plug in 1 to the original equation.
Yeah, because we have a y equals. Plug in 1. So 1 squared is 1. Negative 1 squared, so that's negative 1. Plus 1 plus 2. So negative 1 plus 1 plus 2 is 2. Any questions so far? Okay, so now you got to remember, if you have a slope and a point, how do you find the equation? And that's the y minus y1 equals mx minus x1. So y minus y1, so y minus y minus 2 equals m, which is -1, times x minus x1, and x1 is 1. Let's simplify this a bit. So we can say y minus 2. Uh-oh. I just got a note that says my internet is unstable. So let's hope nothing goes wrong. Y minus 2 equals, multiply the -1 through, you get negative x plus 1. Nothing tricky here. And then add 2 to both sides. And you get y equals negative x plus 3.
Negative x plus.
Any questions at all? Any questions at all on this? Okay, again, a lot of you had different answers. It looked like Cameron did great. So, any questions at all on finding the equation of the tangent line? It's very important to be able to do that. All right, now I want to look at it. So to look at it, you know the tool I like to go to, which is?
Desmos.
Desmos. So let's look at Desmos. And what I did is we have our function y equals negative x squared plus x plus 2. And then we have our tangent line, y equals negative x plus 3. Let me double check. Yeah. And you shouldn't be surprised that it looks like this, because you should know that you have a parabola, and you should know that at x equals 1, and in fact, I should probably zoom in a little bit so we can see the x equals 1. That's better. So at x equals 1, we're at 2. We already found that out. And notice that it really is a tangent line. It touches. Any questions on that? All right. So here's the kind of bad news, and it's something that I don't love about this book, is I think they really should have waited a couple sections before they got to this point, because parabolas are pretty easy to calculate. It's not that hard. But lines are easier. So there are cases where you're going to have the function, and the function is a mess. But lines are never a mess. Right? There's nothing, lines are like the easiest thing in the world to calculate, to plug in. Whereas functions can be really horrible. So parabolas aren't that horrible, but let's pretend that you don't like parabolas. So the idea is I zoom in a lot. Does it really matter whether I'm looking at the line or the parabola? What do you think? If I zoom in a whole bunch like I just did? Not really, okay? And again, for engineers, for example, or biologists or whatever you're doing, if you're off by, 0.0001, it's not a big deal. Do you agree for most things? Okay, whatever you're doing. So the idea here is that if we have some complicated function and we only care about what's going on nearby, then the tangent line is a replacement, and it makes it much easier. And I'm going to get ahead of myself because it's hard to convince you with y equals negative x squared plus x plus 2, or anything we've done in our class. Okay, but let me explain something, and I know there's a few of you that are interested in computers. Negative x squared plus x plus 2 is very easy to program in a computer, to plug that in and have the computer spit it out. What about, let's say it was sine of x. Okay, remember, computers know numbers. They know you could do numbers very easily. It turns out you could do multiplication. You could do addition and subtraction. Those are the things that you can do quickly on your computer if you want to have efficient speed. So say you're making a video game, online video game, and you do not want it to do all kinds of long calculations because things are moving fast and you can't make things move fast and have the whole screen change like you want it to change if you're dealing with long calculations. So let me give you a very simple example. Let's suppose something is sinusoidal. Have you heard that word before? Okay. So in particular, y equals sine of x. Well, it turns out the equation of the tangent line at 0 is just y equals x. Y equals x is very easy on a computer because it just spits out the number that you brought in. Does that make sense? Y equals sine of x is really brutal because it's not arithmetic. So what typically happens is if you have y equals sine of x, you replace it with y equals sine of x, and as long as your angle doesn't change much, it's looking like the picture we're looking at now, where the tangent line and the curve are basically the same. And that's a big, big use of calculus, is to be able to say, well, we have this awful equation that is just going to slow everything down, even with a computer, by the way. Okay, and forget doing it by hand. So I can replace it with the tangent line, which is very easy and very efficient.
Larry, I have a question.
Yeah.
I was thinking about like the tangent line of like cube functions and quadratic functions, and even now if we're talking about sinusoidal, isn't it the definition of a tangent line so it doesn't intersect at any point? But if the curve comes back and this tangent line goes to infinity, say, won't it eventually run into another point of the line?
Okay, so here's the answer to that. Okay, don't worry about the curve coming back because we only do this for when you've zoomed in a whole lot. And once you get out of that little tiny small region, you don't do it. Does that make sense?
Right, gotcha.
So for example, let me zoom back to where we were. You would never use the tangent line to approximate this graph at x equals, say, -1. Right, here's -1 over here. You wouldn't use a line to approximate that. That's stupid. Do you agree? So the line is nowhere near and nothing close to this curve. Okay, you have to be close to this x equals 1 or it doesn't work. Does that make total sense?
Sort of, yeah.
Okay, so when I'm talking about close to the 1, that might be like 1.03. Okay, yeah, I could plug in 1.03 into this quadratic, but I can't do that in my head. Can you? I can, but it'll take me time. And some of you can't. And
Yeah,
those
it'll
who
take
can't,
me
I
just a
guess it would
second, but yeah.
Yeah, but if I take negative 1.02 and add 3, hey, that is what, 1.98. And I'm done. I did that in 1 second in my head. Whereas if I tried to do that with this guy, I can't do that in 1 second. Do you see that?
Yeah.
And is it going to be exactly 1.98? No, but it's close enough. Close enough for engineering purposes, okay? Or most things you care about in life, okay? It does get you in trouble, okay? And let me tell you where it gets into trouble. And that's what basically Newton did. Newton did the linear approximation of life. Sounds great. And then, much later, Newton was long dead. Who came around? Who was the next major physics person?
Einstein, I guess? I don't know.
Yep, and what Einstein really did was say Newton is using a tangent line approximation. And Einstein came up with the real curve. instead of the tangent line approximation. And tangent line approximation works just fine if you're just like playing catch or something. But it doesn't work like near black holes and all kinds of other things like that. So to let you know, it works if you're really close, but as soon as you get into weird situations or far away, you got problems. Does that make sense?
Right. Yeah, I think so. I think what was really bothering me was the definition of a tangent line only intersecting at one point, really. But I guess in calculus we are using 2 points, but they're just very, very close together. So
Okay.
I guess
let
that
me
the whole
fix
idea
the
kind of
definition.
is
It's not
contradictory
not that a tangent line intersects only at one point.
Yeah,
But
I think that's where I
that
got
if you zoom in,
literally.
if you zoom in a whole lot, then it intersects at one point of what you can see. Does that make sense?
Yep. Yeah, no, exactly. I get it now.
Yeah. Okay. Or sometimes it is a line. Like the tangent line to a line is a line and it intersects everywhere, right? And that's a weird special case. But other than that special case, the tangent line, if you get really close, it's not gonna intersect anywhere except the point.
Right. Yeah. I was taking it to infinity, and now I realize the concept is it's a really, really, really small portion. We shouldn't expand that line out to infinity. Otherwise, it may run into other things somewhere else, and then it's not calculus anymore.
Yeah, exactly. Exactly. Okay, so now what we can do is let's go back and let's use it. And I did it in my head, but I want to actually work it out. And so use the tangent line approximation to approximate. Maybe I'll cut and paste. Y equals negative x squared plus x plus 2 at x equals how about 1.004. Any questions on the question? Okay, now I've done most of the work already. Most of the work was to find the tangent line. I already found the equation of the tangent line. Okay, that was y equals negative x plus 3. Now is the easy part. What do we have to do?
Plug in x to the derivative?
Yep, plug in x into not the derivative, but the tangent line. So the answer is y, and it's not going to be equals anymore because it's not equal. It's approximately equal. So my equal sign became curvy, and that curvy equals means approximately equal to. And that is going to be negative 1.004 and then plus 3. Okay, and personally, I don't even need a calculator to do that. I can do that in my head. You may need a calculator. I don't care. You know, that's fine. But negative 1.004 plus 3 is 1.996. Sorry, yeah, 996. Any questions on that? Okay, just note, let's just play around. Is it a good approximation? Let's see. How do you find out how good an approximation it is? Any thoughts? You just plug it into the original function. Because we can do that. That's going to be negative. And then it's 1.004 squared plus 1.004 plus 2. Okay, that's certainly not something I want to do in my head or even by hand. I mean, I could, but I don't want to. Instead, I'm going to use my friend Google. And that's what we get. We get 1.995984. And let's see how good that is. Well, the quick, easy way with the tangent line, we got 1.996. And this way we have 1.995984. Okay, it's really close. Okay, is it exactly? No. Okay, it'll almost never be exactly right. But is it close enough for most applications that you care about?
Probably.
Yeah, we're good to 4 decimal places. Because if you take 4 decimal places, you actually get 1.996, right? Because the 8 brings the 9 up 1, and you get, so this is good 4 decimal places of accuracy. And that's good enough for most things you care about. So if you're doing a video game, for example, and do you think 4 decimal places, is accurate if you're looking at like, 1/10,000th of a pixel that you might be off? That's fine. Does that make sense? So that's how you use this stuff. Very important in all kinds of applications. Any questions so far? Okay, so that's one application, and that's a tangent line. The next one, which we've already talked about, but I want to mention again, is that another word for derivative is rate of change. Let me write that out. So rate of change means the derivative. Okay, you're going to hear a lot of things that mean the derivative, and that is one of them. Okay, so you've probably heard the word rate of change, right? What is the rate of change of whatever? Okay, and that means the derivative. So where have you heard rate of change in the real world? What applications have you heard before? Okay, miles per hour, you might think of that as rate of change. I don't know if I've heard it that way, but maybe. Usually call that speed or velocity. Any ideas? So let me give you lots of examples. For example, the rate of change of the temperature. Okay, that's how fast something is warming or cooling. And if you're dealing with refrigeration or heating, it's very important to understand rate of change. Is that clear? Right, how powerful your refrigerator is, for example.
It's also like chemistry application.
Exactly, in chemistry, okay? You probably, those of you who had chemistry, or if you're in chemistry, you're probably already doing it. You do balancing reactions, but what you often don't do in chemistry at the beginning is talk about not just what the balanced equation is in your chemical reaction, but how fast is it going to happen? Do you know why you don't do that in, say, high school chemistry? And even the first quarter of chemistry at our college? There's a reason.
You need calculus?
Yep, you need calculus. So without calculus, you can't do it. So the rate of change is very important in chemistry, but the reason why you haven't actually done it is not because it's not important, it's because you haven't had calculus yet. But the next time you take chemistry, so if you take another course in chemistry, that rate of change of reaction is really, really important. If the rate of change is really, really fast, what do you get in chemistry? There's a lot of words for it, and it's not chemistry words. Just everyone knows these words. Not seeing y'all jump in. You get a bomb or an explosion. That's what happens in chemistry if the rate of change is really fast. If something blows up. Does that
I
make
was just
sense?
going to say, like, a lot of products and not a lot of starting material.
Yeah, that could happen too. But the big thing you get is you get an explosion. Okay? So you've probably all seen that before. So if you take a match to, a liter of gasoline, that's going to have a very high rate of change. Is that clear? And what's going to happen is it's going to explode. Okay, and whereas if the rate of change is very slow, you don't get an explosion. Okay, you get bored is what you get. You just sit there watching it, and 10 hours later, you don't notice much has changed. Does that make sense? And that's the derivative. So notice, and I want to write this out, for the rate of change, it's a derivative, but it's a special derivative. It's not dy dx. How come? Any thoughts? Because it's dy dt. Why is it dy dt instead of dy dx?
Time is on the X.
Yeah, we're talking about time. And it is very standard to use the letter T for time. No one uses X. Okay, you just don't do that. So if you see dy dt, that's thought of as a rate of change because rate is always by time. Any questions on that? Okay, and again, units are important. The units on the top are y, so whatever you're looking at, and the units on the bottom are time, and that's usually like seconds or hours. Okay, so that might be liters per second. Okay, it could be miles per hour. Okay, but it's going to be a time unit on the bottom, and it's going to be what you're interested in measuring on the top. And you've all seen these units, but you probably didn't think of them like calculus. And realizing this is a dy dt, and that's why miles per hour has to be miles per hour, not just miles, because we're taking the derivative with respect to t, dy over dt is miles per hour. Otherwise, you just have miles. Any questions on that? Okay, so that's very important in terms of, kind of some meaning of these words. A lot of today is vocabulary, by the way. It's just kind of seeing the meaning of the words of the derivative and bringing it together with what you've learned, but never thought of it as calculus. And my guess is you never thought of this as calculus when you were talking about, how fast something changes. Any questions so far? Okay, and unit analysis. Okay, so that's rate of change. Then comes speed, velocity, and acceleration, and we've already talked about those too. Not today, but a different day. I'm going to start with velocity. So let's let x of t, maybe I won't even use that. I think I'll use what they tend to do in the book. Let s of t be the position of an object. Okay, and that could be a car, it could be you, whatever it is. And it's something that's moving along. Then the velocity of the object is, and it's v of t as a standard. And we've talked about this before. What is it, calculus-wise?
S prime of t.
S prime of t, but I'm going to use Leibniz notation. So what is it in Leibniz notation? The hint is there's a fraction. I don't see y'all jumping in. Starts with a D.
Would it be the thing that you just put above this?
What's that? It's not quite dy dt, because y is not our variable. Get close though.
dv.
No, it's not dv dt. There's only one other letter, I think, on this page. No, x isn't on this page.
ds?
ds over dt. And that'll be the velocity. I want to look at this in a way that you may not have thought of before. What are the units for a position? What's a typical position unit?
Meter?
Miles or kilometers or?
Yeah, I'm going to go meters because that's your standard units in science. I know, you like miles, but miles are definitely not standard. So I'm going to go meters. You could do kilometers, but meters is a little more standard for science. If you've had, a little physics or a little chemistry, meters is typically what you use. And then how about T? What are the units for T?
Seconds.
Yeah, seconds. So note the units are ds, and again, d doesn't have units, only s does, and that's going to be meters. I'm just going to use m over seconds. And that should be a nice thing to see because you should be used to that. Are y'all used to that? If you're talking velocity, that's in meters per second. But I'm not sure if you've ever thought about why it's meters per second. And the reason why it's meters per second is the unit system needs to follow the derivative because the velocity is defined as the derivative, and that's ds over dt. Okay, notice you could say it's s of t plus h minus s of t, but the numerator still has just s, right? The units are meters, and then it's divided by t plus divided by h, and the units of h are seconds, and that's why it's meters per second. Any questions on that? Okay, the acceleration. Of the object is, so first thing, the good thing is math and physics people are pretty boring. Velocity is v because velocity starts with a v. Acceleration, they usually use a because acceleration starts with an a. Very easy to remember. A of t equals, now what is the acceleration? Do you remember?
Second derivative?
Exactly, the second derivative. Now, in Leibniz notation, that's d squared s over dt squared. Any questions on that? Notice d doesn't have units, so d squared doesn't have units. S is in meters. So meters on the top. And the bottom is t squared, and that's second squared. Any questions on that? Any questions at all? Okay, so if we know the position, we can find the velocity and we can find the acceleration. So here's an example. Let the position of a, how about a spaceship? B, oops. S of t equal t squared minus 4t plus 2. So find the velocity and acceleration of the spaceship. Let's see if you can do that. Let me give you a minute. Shouldn't take longer. And put in the chat box when you have them. Okay, so let's take a look. So velocity is v of t equals, and you just take the derivative. Derivative of t squared is 2t. And then we go, the derivative of negative 4t is minus 4. That's it. And then we need to find the acceleration of t. The derivative of 2t is 2. And then the minus 4 goes away. It has 0 derivative. And that's it. And again, if you want to write the units, which is probably a good thing, v is in meters per second is standard, and acceleration is in meters per second squared. Any questions on that so far? Okay, when is the spaceship not moving? Okay. So that's really important. For example, if you want to, do some kind of repair or something, or jump into the spaceship or jump out, you probably want to do that when it's not moving. So that's important to know when it's not moving. And from the position, it's hard to tell that, but from the velocity or acceleration, I'm gonna let you see. When is this spaceship not moving? At what time? Yeah, after 2 seconds. So the idea here is we set v of t to be equal to 0. And I could do that in my head, 2t minus 4 equals 0, but let me write it out. So t equals 2. So at 2 seconds, It's not moving before it's moving and after it's moving. And in fact, it's always moving besides that 2 seconds at which it stops. So that's the time at which you want to, jump out of the ship or enter the ship. Any questions on this example? Any questions? Okay, so that's pretty much what I want to talk about acceleration and velocity. I do want to mention something. There's something not very real world about this. What is that? Spaceship? There are spaceships.
We don't usually just have an equation for things that are moving. We have to find that.
Well, you do if you know physics well. Okay, you definitely do if you know physics well. And this would be an example of just gravity affecting it, and that's all. That could happen. Okay, but there's another big issue. And that is that this assumes that it's going just along a line. And ships don't typically just go along a line. Does that make sense? It might orbit something and it might curve a bit. So I want to let you know that what we're doing in this class is not reality yet. Okay, so if you want to be an engineer, for example, first quarter calculus is not enough. What do you need to be able to do?
Integral, maybe?
Well, integrals will happen, but in terms of this kind of example, you need to be able to handle 3 dimensions, right? And not just 1 dimension, right? This has a single dimension of space, but there's more than 1 dimension of space, right? You drive, you go up the hill, you go down the hill, and you make a right, and you make a left, turn around. So it's definitely 3-dimensional. And we're not doing 3-dimensional. Okay, will it ever happen with you guys? For those who want to be engineers, for example?
Sure.
Yeah, the answer is yes. And as long as you stick with it, it'll be me again, but it'll be in the spring. And I am crossing my fingers that I'll be at the board writing with a a pen and explaining, and then looking at your paper and that kind of thing, and giving you a paper test. Let's hope that's going to happen. But that's third quarter calculus. But I do want to note that first quarter calculus, we're not quite in reality yet. So third quarter calculus, you get more into reality. Okay, it's still not perfect, but you get a lot better because you can deal with reality. Is that clear? Okay, and hopefully you do know that we don't live in 1 dimension. Okay, 3-dimension is what we can perceive. Part of my dissertation was 24 dimensions of reality. So I'm not going to get into that. Okay, so any questions so far? Okay, now we just talked about speed, velocity, acceleration. Now let's get into population models. And I think if I remember, we have some biology people. So let's look at population models. Okay, so let me give you, just for bad news, let's look at the worst case scenario of COVID. Okay, so let's suppose that you have, a country where nobody pays attention. They just do whatever they want. Okay, so let's suppose there is a country like that, and right now nobody's got it, but then somebody travels and gives it to someone. What's going to happen? Any thought? So what'll happen if, nobody has it, and then all of a sudden one person gets COVID, first person to get COVID, and you have a society and a government that just totally doesn't care, just lets it happen. Okay, it's going to go up, right? But it's going to go up with what's called a doubling time. So suppose that initially there are, just for fun, there are 2 people who enter the country with COVID. Okay, and then suppose nobody does anything to stop it. All right, then what's going to happen is going to be what's called doubling time. Okay, it's not going to be like in 1 second everyone's going to get it. Do you agree? It's going to take time. So suppose doubling time is 3 days. Then what we want to do is we want to say, well, how do we approximate how many people are going to have it? Okay, so let's suppose we know that in, and we could actually do this, but in 12 days, by the way, how many will have it in 12 days? Let's see if we can figure it out. Initially, at day 0, we have 2. At day 3, 3 days later, we're going to have 4. At day 6, we're going to have 8. At day 9, we're going to have 16. At day 12, we'll have 32. Any questions on how doubling time works? Any questions on that? All right. I'm going to let you know, and this is, I'm getting ahead of myself, but I think it's worth it because it's really important, is you can talk about this as follows. And that is with an equation. And you could say dP over dt is equal to kp. All right, so now let's think about what is dP over dt in words? What does it represent? Where P is the number of people who have it, by the way. So what is dP over dt? If P is the number of people who have it. So people who get it and rhyme time and time. Not quite. So what it is the rate. Remember, the derivative is the rate of change of the population who have it. Okay. So dP over dt is how fast the number of people who have it is increasing. Okay. So it's the rate of change of the population who have it. So what I want to do now is approximate how fast or how the virus is spreading after 12 days or at 12 days. Okay, or what is the rate of change of the infected population at 12 days? Any questions on this? Who would particularly care about the rate of change on a certain day? Who would care more about the rate of change on a certain day than how many people have had it? Any thoughts? Yeah, in particular the hospital admissions people, because that would tell them how many people they should expect to come into the hospital coughing, saying, oh my God, I think I have COVID. You see that? And if that number is too high, then what happens is the hospital is overloaded and we have a disaster. So believe it or not, this is really important in today's COVID times. Okay, this is what we have to keep away from, is we have to make sure that we're not having hospitals overflowing, because they can only handle so much. And you certainly don't want to have to turn people away saying, oh yeah, you're really sick and dying, but the derivative's too high, so we can't, help you. So we have to make sure as society that we have decreased the rate of change or the derivative of the population of COVID as a function of time. Okay, and that has been pretty much what the whole mission has been in the United States. And, have we done it right? I'm not going to be there to judge, but I could do the math. Any questions on that? All right, well, how can we do this? Well, we know that at 12 days, we can say that P of 12 was 32. And we know that P of 15 is what? What's P of 15?
64.
64. Any questions on that? So now we can approximate the rate of change. And this is what we did in the first day of class. How do you do that? Do y'all remember? We done the first day of class. You were testing it last week. Remember? That was the slope of the secant line. So if we want to approximate the rate of change, we take the slope of the secant line, which is very simple, just 64, y2 minus y1, so 64 minus 32, divided by 15 minus 12. And that is equal to 32 over 3. And 32 over 3 is a little more than 10, right? 10 point, what, 66666. How about 67? So what that tells you is that on day 12, we better be prepared for admitting, or at least testing, having around 10 or 11 people enter the hospital with COVID. Any questions on that? Okay, so Are you noticing today is all about applications? And we're ready for the next one. Okay, so we dealt with depressing, COVID, but it's important. It's not just COVID. This happens in Tahoe if you're looking at a invasive species, for example, and you want to figure out how long you have before it becomes a disaster. So you might have a quagga mussel get into the lake. Well, how fast is it going to be spreading? And how fast is it spreading? That's the derivative. Okay, so there's lots and lots of applications of this whole population change, not just COVID. All right, so the last thing I want to talk about is economics. And that is, I want to talk about cost, revenue, and profit first, and then we'll get into marginal. So let me do an example. So suppose you charge, oh, that's right. Suppose you manage a hotel in Tahoe. Okay, well, there's a few things. One is that if you charge a lot more, what do you think is going to happen to the number of people who check into your hotel if you raise your prices? So if you raise your prices, what's going to happen to the number of people in your hotel? It should be obvious.
It will decrease.
It'll decrease. Okay. And that they call this the demand curve. You heard of that before? So the demand curve is going to be X for the number of people who are in the hotel or who check into the hotel. And X is equal to, let's say it's 250 minus (0.3 P), where X is the number of people who check in, and P is the price per night. Any questions on the example here? Okay, the first thing is, what is your revenue? As a function of P. Okay, so revenue is how much money you make per night. So how do you calculate how much money you're going to make? It's very easy. What do you multiply? What times what? It's supposed to be easy. So revenue is equal to, it's going to be the number of people who check in times the price. If you charge $50 and you have 10 people check in, guess what? You made $500, right? You just multiply X times P. Any questions so far? But X times P is going to be X, which is 25 minus 0.3 P times P. Any questions on the math so far? Okay, so the next question is, what is the marginal revenue? Okay, and to get an idea of marginal revenue is you want to say that for every additional dollar that you charge, how much money are you going to make or lose? Does that make sense? And the units of that is revenue per price. So that is going to be the derivative because that's the units for derivative. So first thing, marginal revenue is the derivative. Which you shouldn't be surprised because this is calculus. So now I can just quickly do it. R prime of P. So now what we can do, you have two choices here. One is to use a product rule, the other is to multiply and then take the derivative. In this case, what do you think is easier? What do you think is easier, the product rule or multiplying first and then taking? Yeah, I think this kind multiplying is easier. So if I multiply, and I'm going to do it in my head, I hope you can too. You get 25p, and the derivative of 25p is 25. And then second term will be minus 3.3p squared, and the derivative of negative 0.3p squared is minus 0.6p. Did I lose you on that, or was that I shouldn't do it in my head? Do you need the step? Maybe I'll do that. No one's saying anything.
That's pretty straightforward.
I got it.
So it's 25p minus 0.3p squared. And then I just took the derivative. And there's your marginal revenue. Okay, and what that tells you is if you change the price a little bit, how much do you expect your revenue to change? So by the way, you want to get more and more money, right? Is that clear? So notice that your marginal revenue is going to be positive until when? When is your marginal revenue not going to be positive anymore?
When 0.6p equals 25.
Yeah, or when the price is 25 over 0.6. Okay, so that might be what you want to charge. Okay, and that'd be a good price to charge in your hotel because then you're going to have the best revenue, if that's what you care about. Any questions at all on this idea? Okay, I'm not going to do an example because we don't have any time, but there's nothing really much to say. If we had a cost function, you could say the cost is a function of P. You do the same thing. And you can find the marginal cost by finding the derivative of the cost function. Does that make sense? And if you want to find the marginal profit, you take the revenue minus the cost, and then take the derivative, and that'll give you the marginal profit. Okay, and often you want the profit to be largest. Okay, you know, it depends, but often you want your highest profit possible. Any questions at all on all of these today's applications? Again, today is the application day. On Friday, we go back to finding the derivative of stuff that we haven't found. And some of you are going to hate it, some of you are going to like it. Trigonometry. So we're going to look at the derivative of all these trig functions. And that is going to involve trig. So if you have some time to review trig, you might want to do that between now and Friday so you'll understand what I talk about. I am going to stop share and stop the recording.